In this lecture, we're going to discuss equipotential surfaces. This is going to be section 18.3. So the upshot of a lot of going on in this particular section is an equipotential surface is a surface on which the potential has the same value at every point, hence the prefix EQUIP. At a point where a field line crosses an equipotential surface, the two are perpendicular. So you're seeing the electric field line here. You're seeing a cross section of an equipotential surface, which actually is more in 3D, but since we can't draw that, we're going to go with the 2D. Where these two intersect, you are going to see that they will be perpendicular to each other. Also, when all charges are at rest, the surface of a conductor is always an equipotential surface. And all points in the interior of a conductor are at the same potential. So let's take a look at the description here. Let's take a look at this video.
In this demonstration, I'm going to left a spoken wheel inside this nap spherical shell. On the other half of the shell,
Okay, I thought that one was pretty cool. Okay, so those are a couple of interesting videos there for you to examine or perhaps play back if you wish. So field lines are going to help us to visualize electric fields. In a similar way, the potential at various points in an electric field can be represented graphically by equipotential surfaces. So an equipotential surface is defined as a surface on which the potential is the same at every point. In a region where an electric field is present, we can construct an equipotential surface through any point. In diagrams, we usually show only a few representative equipotentials, often with equal potential differences between adjacent surfaces. Now, no point can have two different potentials. You can have one point that is at one value and that same point be at another value. So equipotential surfaces from different potentials never touch or intersect. So the potential energy for a test charge is the same at every point on a given equipotential surface. So the electric field does no work on a test charge when it moves from point to point on such a surface. So it follows that the electric field can never have a component tangent to the surface. If you did, then work would be done on a charge moving on the surface, and that's not what we observe. So therefore it has to be perpendicular to the surface at every point. And field lines and equipotential surfaces are always mutually perpendicular. In general, field lines and curves and equipotentials are curved surfaces. For the specific case of a uniform field, in which the field lines are straight, parallel, and equally spaced, and the equipotentials are parallel planes perpendicular to the field lines. So let's look at these arrangements of charge. We have a single positive charge, and we have cross sections of equipotential surfaces at 20-volt intervals. Here we have an electric dipole. We can see the equipotential surfaces here surrounding each of those. We have two positive charges here, and we can see the equipotentials surrounding these as well. So this concept of equipotential surfaces is particularly important in understanding the electrical behavior of conductors. So remember that a conductor is a material that allows charges, usually electrons, to move freely about in its interior. We can now prove that when all charges are at rest, the electric field just outside a conductor must be perpendicular to its surface at every point. We know that the electric field is equal to zero at every point inside the conductor, otherwise charges would move, which would violate the assumption that they are at rest. Right at the surface of the conductor, we will also require the component of E that is parallel to the surface be zero, so charges don't get pushed along on the surface. But you can have a perpendicular component. The charges cannot leave the surface, so the perpendicular component of the field cannot cause the charges to move. It follows that in an electrostatic situation, a conducting surface is always an equipotential surface because it can only have a perpendicular electric field. If you had a parallel component, you could see something move here, which would mean work would be done. So we can draw equipotentials so that adjacent surfaces have equal potential differences. Then in regions where the magnitude of E is large, the equipotential surfaces are close together because the field does a relatively large amount of work on a test charge and a relatively small displacement. Conversely, in regions where the field is weaker, the equipotential surfaces are further apart. If we want to state this quantitatively, then we suppose that we have two adjacent equipotential surfaces separated by a small distance with a potential difference of delta V. If delta S is very small, then the electric field is approximately constant. So the work done by the electric field on a test charge that moves from one surface to the other in the direction of E is going to be equal to Q prime E delta S. But from the definition of potential or potential energy per unit charge, this work is also equal to minus Q prime delta V. So you put the two expressions together, and what you come up with is that the electric field is equal to minus the change in voltage over the change in distance. So the negative sign reflects the fact that when a charge moves in the direction of the electric field, its potential decreases. The ratio is sometimes referred to as the potential gradient. If you want to split it up into dimensions, then you could take delta V divided by delta X for the electric field in the X direction and do the same for the Y and the Z components. The electron volt. The magnitude E of the charge of the electron can be used to define a unit of energy, the electron volt. It's pretty useful when you're looking at atomic and nuclear systems to quote things in electron volts. So when a particle with charge Q moves from a point where the potential is VA to a point where it is V sub B, the change delta U in the potential energy is going to be equal to delta U is equal to Q times the difference in voltages, which is equal to this. If the charge Q is equal to the magnitude E of the electron charge and the potential difference is 1 volt, the change in energy potential energy here is equal to this. And that quantity is defined as the electron volt. A lot of times multiples of that is what's used or what is quoted. So when a particle with charge E moves through a potential difference of 1 volt, its change in potential energy has magnitude of 1 electron volt. If the charge is an inner multiple of E, such as N times E, change in potential energy in electrons volts is N times the potential difference in volts. So for example, an alpha particle which has a charge 2E moves between 2 points with a potential difference of 1,000 volts. Its change in potential energy is 2,000 electron volts. So although we define the electron volt in terms of potential energy, we can use it for any form of energy. I mean, energy is energy, so it could be kinetic energy. When we speak of a 1 million volt electron, we mean an electron with a kinetic energy of 1 million electron volts, which is this. And this video here is showing you the capacitor bank at the Sandia National Laboratories Z machine, and that is discharging. It's the world's most powerful X-ray source. So we're looking for high radiation research here.